Okay, I want to talk about some exponential growth and decay problems. Okay, so I think one more video should do it and we'll be done with that. Chapter 6. Okay, I'm taking from John Grimma's stuff in section 6.8, number 9. The population of a city is expected to triple. I've written in here every 20 years. Okay, the city currently has 10,000 residents. How long until the population is 50,000 people? Okay, here's what we're going to do here. The first thing we see, the independent variable here is going to be what? Time. So we're going to see t is time in years. After the initial year. Okay. We didn't have any particular initial year, but this t is the amount of time that will have passed. Okay, and I'm going to have population, which will be a function of time, so I'll write it this way. We'll have this be what? The population after t years, or at the end of t years, if you wish. Okay, the population, of course, is in this context the population of the city. Okay, we need a law governing the growth of the population, so we need to write that. And I'll show you how to do this. Okay, what you're going to start out here, you have your initial population, which was what? 10,000. And then it's being multiplied by a factor of what? What does it mean to triple something? It means to multiply it by a factor of 3, right? If you've got $7 and you triple your money, you're going to have 3 times that much. You're going to have $21. Alrighty? So the point is it's being tripled over and over again, possibly, okay, for as long as this model holds. So you're multiplying it by a factor of 3. How many times are you multiplying it by a factor of 3? Well, that depends on how much time has passed, right? Well, if you think of this in terms of years, what would happen if in 20 years you'd have a population which is 3 times 10,000? In 40 years, right, you would have multiplied by 3 2 times, right? Does that make sense? In 60 years, you would have multiplied by 3 3 times. Do you see what we're actually doing when you're multiplying by 3 over and over again? Of course, it's like what? Taking 3 and raising it to a power. What you're doing is taking the time in years that have passed and dividing that by 20. That gives you your exponent here. See if that doesn't work here. If t is 0, 0 divided by 20 is 0. 3 to the 0 is 1. 1 times 10,000 is 10,000. That means your population at time 0 is 10,000, which makes sense. That's the initial population. If t is 20, then 20 over 20 is 1. 3 to the first power then, so which is 3. 3 times 10,000, 30,000. If t is 40, 40 divided by 20 is 2. So you're going 3 times 3, you're going 3 squared, which is 9 times your initial 10,000. So that's 90,000 again, and so forth. Okay, so what this thing actually represents is the number, can I use this terminology? This is the number of tripling periods, right, because this was in terms of tripling periods that have passed in 2 years. Okay, and that's the number of times you would be tripling then, right? Therefore, it's your initial population 10,000 times 3 to that power. So this is the governing law for this, right? Now, remember here, I don't know, maybe I should use parentheses on this part here. Remember that exponent is only being applied to the 3, right? You actually compute this first and then you're multiplying by the 10,000. Okay? So don't raise 10,000 or 30,000 to the t over 2. I've seen people do that, just as a warning here. Okay? All right, I hope that makes sense. Now let's go ahead and talk about our particular problem. Okay? Our particular problem is what? I've got a population that's given as 50,000. Okay? And what am I looking for? I'm looking for time t. Okay, I'm looking for time t. So here I'm trying to solve for t in this equation, right? Solve for t. Now you notice, what is t? T is up there in the exponent, right? It's an exponent. So what are we going to be thinking in terms of? Logarithms, right? Right? Logarithms are exponents. When you're looking for an exponent, logarithms are the tools you use. Okay? Divide on each side. Here's the thing to do. Isolate the exponential, the pure power function here, by doing the following. Divide on each side by 10,000. Okay? I'm running out of room here, so I'm going to do this mentally. So if I divide 10,000 on this side, that becomes the factor 1. 10,000 on this side, it becomes what? 5. So I've got 5 equals 3 to the power t divided by 20. Now that's what kind of an equation? That's an exponential equation. We've seen solutions like that before. This would be equivalent to, or at least imply, it would be equivalent to, but it's sufficient to write implies, that what? T over 20 is the logarithm base what? There's only one base here. Remember our terminology with exponential functions. The only base is 3 here. The value of this exponential is supposed to be 5. So the exponent should be the logarithm base b of 5. And then, that's the exponent. Now let's use maybe our change of base formula with the natural logarithm. Okay, I can squeeze that in a little bit better. Okay, so this is a number that we'll calculate carefully with our calculator. Make sure you get the right calculation in your calculator. And then to isolate t, I'm going to multiply this by 20. What we're really finding here then is the population has actually grown by what? A factor of 5. And if we're tripling every 20 years, we're wondering how long it takes, what? How many times you have to triple, right, to get 5 here. It's going to be a fraction of a tripling number. Anyways, here we go. Let's go ahead and do this. I didn't say where to round it. Let's just say rounded near to, I'll say this in the exam, round to the nearest tenth of a year or something like that. You don't have to be quite as careful when you're talking about time as when you're talking about an, oh, never mind. I'll let you know. Okay, so I put the calculation in here like that very carefully here. 29.3 years, it looks like. 29.3 years. Now, after you're done here, go ahead, maybe a quick double check. Does this seem like a reasonable answer? Okay, what would happen in 20 years? Just as a double check here. 20 years, you would have what? The population being tripled. So that would be what? 30,000, right? In another 20 years, you would have, in 40 years, you would have it tripled again. It would be 90,000. Okay? The population we're talking about is 50,000. It's somewhere between these two, right? So our answer should be somewhere between 20 and 40. Okay, and it turns out 29.3. Okay, maybe a little bit closer to the, it's almost smack dab in the middle, but a little bit closer to the 20 than the 40. Anyway, okay, alrighty. Now, I just want to mention here, in some of John Grimma's solutions here, he's writing everything in terms of basically continuous compounding. Every exponential problem can be turned into a continuous compounding problem. What I'm doing right here, I'm showing you the method I would use here. I'm going to come back, so I'm just saying this is 1. Okay, I'm going to come back and revisit all this stuff again using a sort of a continuous compounding approach instead. Okay, so we'll be looking at the same problems in 2 different ways. All right, let's try another problem. Okay, hope that made sense to you. All right, a bacteria colony grows by a factor of 4. What would you say that? Doubling is growing by a factor of 2. Tripling growing by a factor of 3. How about a factor of 4? Quadrupling? Okay, some people might say that. Now, it could be, any number here. It could be growing by 4.273 or something, But I had an easy factor here, factor of 4, every 2 hours. Okay, so these are important parameters here you want to pay attention to. If there are 5,000 bacteria initially, answer each of the following. Okay? Now, remember, if something is growing by a fixed factor in every fixed time period, it's got to be exponential growth, right? Okay? That's the hallmark of exponential growth or decay here. Decay would be a factor is somewhere between 0 and 1. Okay, anyways, let's get to it. Write a formula for the bacteria population as a function of time. Time is t. What would the time period be naturally in this problem? We'd be looking in terms of hours, right? Because that's how the original parameters were expressed here in terms of hours, right? Okay? All right. Now the population as a function of time. So this is population after t hours. Okay? Can you go ahead and write an equation for the population as a function of time? Okay, this is a skill you're going to need for the exam here. Well, here's what you do. You have an initial population as 500, and that's being what? Multiplied by a factor of 4 repeatedly. I'll go straight to parentheses this time. Okay, in our previous problem, we were multiplying by a factor of 3, right? Tripling. This is a factor of 4, so I'm going to have 4 as my base this time. And it's every 2 hours. Okay? I claim my exponent's going to be t divided by 2. What would this represent? Okay? This would count what? The number of quadrupling periods that have passed in t hours, right? So if t is 0, you can see that's going to be a 1 factor. That's initial population. If t is 2, 2 divided by 2 is 1. 4 to the first power, you would have multiplied by 4 just 1 time. If in 4 hours, you would have had what? The exponent being 2. You would get 4 squared here. You'd have multiplied 500 by 4 2 times, and so on. I hope that makes sense to you. I hope you're starting, even now, even though we just began this stuff, start seeing the pattern that's forming here. In fact, I think I'll actually box this in here. Remember how I'd like you to box in your final answers. Okay? Let's go ahead and perform a calculation this way. This is one I made up, so this is not one of John Grimm's here. What's the population after 3.5 hours? Let's go to decimals. So that I would just be trying to find p of 3.5 and just round to the nearest whole bacterium, right? Right? You don't need, parts of bacteria here. That's no model's perfect anyway, so you have to understand this isn't going to give you a perfect count or anything anyway. Okay, now this is what I got for my round number here, 5656.85. We'll just round to the nearest whole bacterium. Okay, you're not going to have part of a bacterium. Okay, so we shall go ahead and say this. Okay, and this would be counting that many bacteria. Okay, all right. Now nobody claims this would be the perfect number. It's just a model. Okay, that seems to work well in real life. Okay, now let's do something else here. Let's come back. This question is asking you how long it would take for the population to reach 100,000, round to the nearest tenth of an hour. Okay? All right, John Grimm may have had you answer differently here, but remember, I'm going to be the one grading you, so pay attention to the way I ask the question here, how I want your answer. You say I have 100,000 as my population. I've given you p now, and this is going to be what? 500 times 4 to the t over 2. Okay? So we know what this side of the equation is. Now we're looking for t, right? Different from part B there. Okay, how do we solve this problem? Well, the first thing I'm going to do here is divide by 500 on each side. So take 100,000, right, on your calculator. Make sure you get the right number of zeros and divide it by 500, and it goes 200. So we've got 200. What does that 200 represent, really? It represents the, what, factor by which the population has grown. You're saying 200 times. How long does it take to get 200 times the original population? Okay? Now, can you rewrite that as an exponential equation? That'd be a logarithmic equation. It's already an exponential equation. The exponent, t over 2, with the logarithm base 4 of 200. And if you want here, we could say t is 2 times the natural logarithm of 200 divided by the natural logarithm of 4. I'm jumping in there using the change of base formula. You could have used log instead if you'd prefer to do that instead of ln. Just be consistent about it here. Okay, let's see what we get here. I get 2 times ln of 200 divided by ln of 4. And I get this. I get 7.64. So we would just say approximately 7.6 hours. There I rounded to the nearest tenth, didn't I? Like I said, tenth. Okay, 7.64, round to the nearest tenth. Go to the hundredth. Is that 5 or more? No, so just truncate it. Just cut it off there. And we should be good. Okay, here's another situation here that we're going to deal with, radioactive decay. Okay, in our previous problem, we had exponential growth. This is actually an example of exponential decay. Let's talk about this particular problem. So the amount of something that you have actually gets smaller over time rather than larger. So instead of growth, it's shrinking, right? Okay. The half-life of a certain element is 100 years. Okay. A 40-ounce sample of the element is obtained. This is 12 from that section, 6.8 by the way. So you got 40 ounces initially. How long will it take until just 10 ounces of the sample are left? Until 7.5 ounces are left. Okay? All right. Now, here's what we're going to do. T is going to be time again. Time in years. Okay? You can see why I'm taking years this time initially. That's in years. Now let me show you. A, I'm going to call this A of T, is the amount left after T years. And we'll explain what half-life is, what's going on here. Okay, just get these initial parameters down here. Now I'm going to do this. A at 0, I like to sometimes go like this. A naught, A subscript 0. This makes you think of a constant, right? What is a constant for this particular problem? This is what? This is 40 ounces. Okay, the amount here after T years, I should have mentioned that. I'm out of room now. This is the amount in ounces. I'll squeeze it in there. It doesn't look good. Sorry about that. But it's the amount in ounces after T years. Okay? Okay, do you see how I squeezed these out from the problem here? Created some definitions and stuff that are natural. Okay, now let's talk about what happens here. What's half-life? What's radioactive decay? It is simply this. This actually happens in radioactive materials. Okay? What it says is that if the half-life is 100 years, this means every 100 years, the amount of the radioactive element you have gets cut in half. Now, this is a continuous process, so it doesn't suddenly, you don't have 40 ounces of the radioactive material, and then 100 years later, suddenly you have 20, right? It decays over time, okay? But the idea is if you measure the amount initially, and you measure the amount you have 100 years later, it's always been cut in half, okay? It's cut in half. You can see here that what we're doing is getting exponential decay, right? Let's go ahead and try to get a formula for this. We'll see how it works here. A is a function of time. Well, the initial amount we had was what? 40 ounces? Okay, this is in 40. Now, here's the idea. It's getting halved over and over again. So in 100 years, what's going to happen? You're going to have half of this. You're going to have 20. How about another 100 years passes? It's going to be halved again. So you'd only have 10. Well, that answers that question, doesn't it? Okay, in another 100 years, you'd only have 5, and so forth. Does that make sense? So every 100 years, it's getting cut in half. But again, it's a continuous decay. It's, like I said, it's not sudden. Okay, Can you write the equation then? Do you see I'm halving over and over again? Okay, halving over and over again. Alrighty. All right, can you write what the exponent would be? T divided by 100. I hope you're seeing the pattern that's going on even in this stuff, right? What would this represent? This would represent the number of half-lives that have passed in T years. Okay? In 100 years, 100 divided by 100 is 1. 1 half-life has passed. In 200 years, 200 divided by 100 is 2. 2 half-lives have passed, so you've halved twice. Okay? Does that make sense? Okay? I hope this pattern's emerging here. You see what's going on here. This, if you'd rather have decimals too, you know, on your calculator, I'm sure you will here. Or you could actually put this down in the denominator with a 2 in the denominator. But let's go ahead and write it either way here, like this, okay? I like to keep that half in there because half-life and all that. Okay, does that make sense? Okay. Now, the first question here was 10, okay? Alrighty. Okay. What's dividing both sides by 40, right? Do you see I get 1/4 on this side? And I'm going to bring this back to a half here. Okay. Does that make sense? Okay. Look good. Okay, divide by 40 on each side. 10/40 is really 1/4 or a quarter. Wait a minute, I see a convenient common base. That's really a half squared. Look good? Now, remember, every exponential function is 1 to 1. Since these have the same base and they're equal, those exponents must be equal also. So I've got 2 is equal to t over 100. That implies that t is 200 years. Okay? By the way, John Grima in some of his questions will throw you off saying round to the nearest hundredth or something, to 2 decimal places. Sometimes you don't need to do that. Okay? All right? Alrighty, how about the next question where it says 7.5 logarithms? Okay, so let's go ahead. That's that part. 7.5. This is 7.5 is less than 10, right? So this is going to take a little bit longer here. It's going to take more than 200 years. Okay, but you see that would be my equation. Okay, and then I'm going to divide both sides by 40. And then I'm actually going to do the following. I'll write this as a logarithmic equation. 10 over 100, that's the exponent, is the logarithm 0.5 of 7.5 divided by 40. Notice how I'm just avoiding doing arithmetic here? I'm going to use a common logarithm this time. 7.5 divided by 40 divided by the logarithm of 0.5. Okay, right there I just used my change of base formula, right? This time I'm using the common logarithm. Now to isolate t here, don't forget I have to multiply on each side of this equation by 100. So this is just a fancy number here. It's easy to solve for t. Multiply by 100 here. And this way, I don't have to do any real arithmetic. Okay. Just writing down forms and stuff, but I have to be careful, right? I want to make sure I put it in my calculator correctly. Okay, so let's do this. Okay, I'm going to go 100 times log, just log, 7.5 divided by 40. Okay, I want to close that off because that's the numerator. Then I want to divide that whole numerator by the logarithm of 0.5, like that. Okay. And I get 241.5. Okay. 241.5 years. Okay. Like we said, it's got to be more than 200 years because to get down to 7.5, That's going to, in 200 years, we had 10 ounces. So we're going to need a little bit more time here. And I would say, I don't know if I even said this, round to the nearest tenth. That's what I did. He might have said to the nearest hundredth or something, but the rounding part's easy. Okay? I hope you understood that then. Does that look good? Okay. Understand the main thing. You got to, well, not just the main thing, but you got to understand that. Otherwise, nothing else really matters. If you mess up this part, you know, how are you going to get the rest of this? But anyways, I wanted to show this final formula here for radioactive decay. Okay? The amount after time t is the amount you have initially, times 1/2, if you want 0.5 there, to the t divided by h. What is h? H is the half-life. T is time. Okay? These would have to be expressed in the same units. Maybe they're hours. Maybe they're years. You know, sometimes even seconds. Some radioactive materials and things decay very quickly. Okay? All right? And what would this represent? The number of half-lives that have passed in t years. So you're going to take half and raise it to that power, multiply by whatever your initial amount was. Okay? So this is our boxed-in formula there. That means it's important if you run into a radioactive decay problem in your work there. Okay? Now, like I said, I am not using the continuous compounding model that John Grema did for these problems, but I will be doing that next. So I've got another video to put up on this, okay, where I'm going to revisit these problems and look at it from that point of view. In the meantime, I think this should be quite helpful. Okay?